of you who don't know me, I'm Graham Smith from the University of Birmingham, and I'll be the chair this morning. And our first talk this morning is online. We have Emilie Ishida from the Université Clermont-Auvergne. And over to you, Emilie. Take it away. We're looking forward to your talk.
Thank you. Thank you. Just to confirm, can you hear me okay?
Yeah, we can hear you great, loud and clear.
Yeah, okay, good. So thank you, everyone. Good morning, good afternoon, good night, depending on where you are. I would like to thank the organizers a lot for inviting me and allowing me to present this online. Next time, I definitely hope to be presential with you all. And so for the talk today, I'm going to talk a little bit about recommendation systems in the broader sense. We have been listening in the last 2 days about different types of recommendation systems. And I wanted to, and all of these tools, they are they are great, and they can help us a lot in the scientific tasks we have to perform. But in order for them to, so we can optimize their use, we need to have a very clear idea of what is our scientific objective in mind, and build, how do I say, a loss function or an environment that will actually optimize the use of these tools for the purpose we have in mind. So today I'm going to go through 2 different scenarios where recommendation systems are used, and they have been proven to be successful. And I'm going to talk a little bit about the caveats and the algorithms that is done that are used in these scenarios. So the talk is divided in 2 very different parts. I first going to talk about supervised learning, and another I'm going to talk about unsupervised learning in the context of CTF and LSST for the future. But before I start going to the very practical issues, I always like to remember where we are coming from. So we are coming from a tradition of very small and especially very personal data sets. So a telescope has never been something very cheap. It was something that very few people had access to from the beginning of the observational astronomy. And normally, what I mean with this is that personalization, designing an experiment in our case for the exact person who is performing the experiment, has always been in the center of our analysis. From the beginning, this was like one very lonely guy who stayed up all night at the observatory and had absurdly a lot of data from 1 or 2 very specific objects. So this is where historically we are coming from, and this is the tradition of a relationship with the data that we inherited from them. With big data and the new telescopes, what changed? So things now are less romantic, some would say not. But now we have super big telescopes, which give us access to a lot of data. This data needs to go through a machine that will filter the data for us before we can actually look in the data ourselves, because there's too many data. So this first step changed, because now it's not a direct relationship ourselves with the data. It is necessary to have a machine in the middle of this, but also we alone, one person alone, might not be able to give meaning to the data. So now we have groups of scientists who will work, but the goal of everything is still very similar to what it was in the beginning, which is satisfy the small group of people that can give meaning to that data that is there. And this exercise has not changed. So this personalization of recommendation system, or this extra layer of complexity that was introduced by the big data, is not only for us, it's for everyone. It's being used in many different contexts. So just to give you an idea, the Oracle, Wikipedia says, a recommendation system is a subclass of information filtering system that provides suggestions for items that are most pertinent to a particular user. So the entire definition and concept of a recommendation system means that you can take your code or your system and personalize it for the need of each individual user. And my goal in this talk is to convince you that this is the only thing we can do in the long run, and how we can do that. As I was saying, the applications of recommendation systems are all around us. So this is not the only application that we have. And so recommendation systems are just machines that look at your data, your historical of behavior, and try to predict what you are going to do next. They are found in Amazon. These numbers are a little bit old, but a few years ago, 35% of Amazon's revenue is given by things that they recommend you to buy, not things that you went there to buy yourself in the first place. 75% of the users of Netflix select films that are actually indicated by the recommendation system. There are more obvious applications of this, like spam email filtering, for example, and obvious tests of new drugs, because you want to have normally a very specified for a different type of condition that can differ by individual, and you have to understand how each individual will respond to that particular thing. Not really in astronomy, because for us in astronomy we have a lot of photometry, but we need training samples. Training samples means labels, and we have to understand how to recommend the next spectra that's going to be taken. This has already been said before, so I'm not going to spend too much time on this. The interesting thing in my point of view of all this is that in the era of big data, all of these recommendation systems are trying to make decisions based on very small number of information. Because even if we have a lot of data, labels are still expensive, and getting precise information is still expensive. So all of what these things are doing are trying to predict the behavior of future classifiers or consumer, or of the prediction of some system based on partial information. So they're trying to extrapolate whatever is happening right now. So I'm going to start from the supervised learning part, and I'm going to talk a little bit about algorithms. So if you have seen my talks, I know you know this slide. I'm going to be very fast on this, but it's important for context. There are different types of active learning, and one of which is the most used is a pool-based active learning, which means that these are the algorithms behind the recommendation system. So you start with a labeled pool, you train your machine learning model, you have very bad initially boundary conditions, and then you classify your entire pool of unlabeled data. Then you have a recommendation strategy that will tell you which of the objects for which you do not have labels are more informative to your model. That object then is given to a human or a machine who will give you a label. In our case, someone who will take a spectra for us, and then you put back the training and you do this again. So the idea here is that if you remove the human decision from the process of constructing the training sample, you will increase the efficiency of the algorithm in choosing objects which are informative for that classification exercise. And this is supervised learning. So remember that you have a training sample, and what is the labels, what is class A and class B is well defined, and there is no problem with that. So we have this algorithm was applied by the Cosmostatistics Initiative in one of their residence programs in 2017. This is data from the old challenge data. What you see here is that how the representativity between training and target sample increases as you go through this loop. So in the first iteration here, you only have 10 objects in your training sample. So with only 10 objects in your training sample, you see that the training, the red ones is the small initial training. The yellow one is the complete training sample from the old challenge data. and the blue one is the target sample. So first we see that there is a lot of non-representativeness here because the distributions actually don't match. And in the beginning, the red one, which are the small training sample that you have, it doesn't tell you much. But you see that as you evolve through the iterations, in the end, the red curve becomes much more similar to one distribution or the other, depending on the survey strategy, the learning strategy that you choose. So if you keep doing what you are doing right now, like keep asking for things that are close to type 1As, you will actually end up with a very similar training sample that you have right now. The middle one is if you randomly take samples from the pool sample, so you don't make any formative decision, and the other one is if you use uncertainty sampling. So you will see that the end distribution of these plots are basically the same, but the point is that uncertainty sampling quickly learned that you don't need to query things in this region of the parameter space because there is nothing to learn there. The distributions do not overlap. So this was the first exercise done on simulation, and it was quite interesting. And then the next step would be to apply this to real data. I am not going to talk too much about this because Anais has a talk later today, and she's going to talk more about the Think broker and how the systems are incorporated in there. But just so you have an idea of how this representativeness issue evolves through the iterations. These in the left side hand plot, you have distributions of disease data from ZTF. This is real alerts from ZTF, cross-matched with SIMBAD and TNS. So you see that in the beginning, you have the probability distribution of non-1As are on orange, and of 1As are in blue. And you can see that in the beginning, they are quite mixed. If you follow a random sample strategy, the distributions has a very different shape than what happens if you follow an uncertainty sampling strategy, if you make an informative decision of choosing these objects. And then the query, the answer comes, okay, suppose that I am following this recommendation system, I am following these algorithmic strategy. What are the objects that are going to be queried every time that I do? So in the end, what will my spectroscopic sample be? And what we learn from this real data is that in that scenario, by definition, 50% of the objects you query will be 1A, because in this uncertainty sampling, at each iteration, you are asking for a spectra for an object, or the object whose probability is closer to 50%. So by definition, 50% of the time, you will have a 1A. The other 50% of the time, you will have things that are easily mistaken by 1A. So in this particular exercise, you see that in the beginning, stars dominated the data set. But after 300 iterations, you would have a lot of other supernova objects and also a few stars and multiple objects as contaminants, not contaminants, but as the real class of the objects that you query. But obviously the world is not that simple. So all of these exercises that I showed you before, they didn't take into account any observational constraints. And you see, and obviously we have many more things that we have to take into account. So we have to take into account that each time in the real scenario, if you are in production, every time that I'm going to ask for a spectra, I have a window of opportunity, which means that the object needs to be bright enough for me to be able to sample it. And since these objects are evolving, they are coming in and out of the queried sample. So sometimes I can query them, sometimes I cannot. So we need a way to estimate the brightness of the object at a particular time. It was also a subject of a previous talk. We have multiple instruments, so I want to take a spectra, and I have one 4-meter telescope, one 8-meter telescope. I have a little bit of hours, different types of hours in them. So all of these have to take into account, and also take into account that even for a given object, the evolving cost increase or decrease because the objects are getting brighter and dimmer because they are transient. In the computer science language, these are called snapshot constraints. I don't know how to pronounce that correctly. But those are all constraints that need to be taken into account at the same time when you make your batch of queries or things you are going to ask for. So we did this also with the old 2010 challenge data. We tested a bunch of different learning strategies, including now we are not querying only one thing, we are querying many different things at a time, and the results basically don't change. So what you have to understand from this plot is that on the y-axis you have the classification score. So this is just a combination between completeness and recall. So you want this to be 1. This is the only thing that matters. And all of these different curves are different learning strategies, very complex ones and very simple ones. And the thing that we learned from here is that the uncertainty sampling, which is the most simple one, performs as well as any of the others when you put into account all of these complexities in the data. So it doesn't matter if you are super complex or not. It's better to stay simple. And this is the same plot, equivalent plot to what I showed before, but now it's the same data, the same plot, but now taking into account all of these different constraints. So what you have to compare is the gray one is the validation distribution, and the two different ones are two different things that are queried by different learning strategies. So you see that they are pretty similar, but the random sampling is still different. The batch entropy still differentiates a little bit more because it focuses on specific regions of the parameter space. So now there is obviously, although beyond all of this complexity, one other thing that we also have to take into account is that why we are doing this. This is why I was talking to you in the beginning. So in the context of supernova cosmology, we are doing this because we want to do photometric supernova cosmology. So we don't want any classification, good classification results. We want a classification result that will allow us to have better cosmological results in the end. So the idea is you have a training sample, and all of this process that I told you about it's going to optimize the construction of this training sample. You have a learning algorithm, you put these two together, and here it doesn't matter if you're using a deep which learning algorithm that you are using. Like the algorithms will differ between themselves, but they will all perform better with a better training sample. So if you optimize this, you train your algorithm, and then you have a machine learning classifier, you classify your supernova candidates. These are all full life curves that you think might be used for cosmology. And then you have a set of photometrically classified supernovae, and from this you can get your cosmological results. So the idea is if you optimize this, it should influence that somehow. And the question that we want to ask now is, every time that I change one or a batch of objects in this training sample, does that impact my cosmological results or not? Because if I added 100 spectra in this training sample and my cosmological results didn't change at all, you probably don't need those spectra. So this is where all respect project is built around. I'm not going to talk too much because Alex already gave you a very deep explanation of respect yesterday. But just to emphasize that respect is a recommendation system for spectroscopic follow-up with the specific task of identifying at each iteration of the active learning loop, thus my cosmological results are affected by a different classifier, yes or no. And in that sense, the fact that we are not using probabilistic classifications is because we are assessing what I would say is an extreme case. So if we don't take probabilities into account and we are completely wrong, it would be the maximum possible effect you can get in the cosmology results. Any other pipeline would be less sensitive to that error. Let's put it like this. And also, all of this is being developed to be fast and computationally efficient enough so we can put inside this loop and run this many times during the day. Because all of these loops needs to be done during the day, and in the night we have a new model that is going to treat the objects that are coming. So what is next for this? So I believe that meaningful, so I think that from this part, the thing that I wanted to remember is that meaningful supervised training, even with a well-defined objective, as it is the supernova cosmology, the supernova photometric cosmology case, which is a very clear classification binary exercise, a very clear final cosmological result. It's non-trivial in the realistic scenario, and you have to take to be careful about that. Feature extraction is still a problem. Indeed, because I'm using simple random forest classifier, so feature extraction is necessary, and it's still one of the huge expenses that we have on this that need to solve. And if preparing for LSST, there are two things in order to have any active learning working in production, which is this science-based recommendation system needs to be integrated with other pipelines, and that we are starting to think about that. And also, every time that, not every time that you have a new label, but every time a new informative label is available, you should be able to automatically retrain these algorithms. So this is where we are right now, and a lot of the research that I have been seeing on active learning is based on variations of pool-based active learning, and there are a few which I think is worth mentioning. For example, every time I talk, I always say that I'm using a very simple random forest. I am not a deep person at all. But Mike has a very nice work, for example, using active learning in the context of convolution neural networks to improve galaxies reclassification, which is super interesting because they use the advice of the volunteers as labels and try to understand if the results change, if they give the volunteers different galaxies to look at, which is super interesting. And another point that I think it's important to make here is that there are more than pool-based active learning. So from the statistical perspective, if you look at these optimization problems, what we are trying to do is optimal experiment design, which means that you want that the probability of your loss function will depend on your previous results somehow. The pool-based active learning is just one way of how this dependency can happen, but there are other ways that this dependency can happen. So one example is generative and sequential active learning. So this is a very interesting work from a few years ago where they actually use active learning to search for regions of the parameter space that are lacking information and use that region parameter space to generate more simulations in a forward modeling context. So this is also one of the possibilities, and I think it's a very interesting application of all of this stuff that we should also have to keep into account. I know that I have 6 minutes left, so I will just very quickly try to tell you how these things can also be applied to the unsupervised learning scenario. So I told you that in the supervised learning case, we had a very well-defined problem. So it's an A-B binary classification with a very clear scientific question in the end. For the anomaly, in the unsupervised case of anomaly detection, things are much more complex. So again, I'm going to go very quickly to this because I already told you about this. But you start here in your data sample, now in the unsupervised learning case. You start here, you build, in this case, isolation forest thing. And then this algorithm is going to give you a list of anomaly scores. So you take the object with higher anomaly score and send that to a human. This human will tell you, is this an scientifically interesting anomaly, yes or no? And here I'm using the definition that Konstantin was using, that An anomaly is something that is scientifically interesting, and an outlier is just something that was identified as a statistical knot from that distribution. So if the human tells you, yes, this is an interesting anomaly, I want to know more about this, nothing changed. But if the human tells you, no, this is not interested, I am not interested in this type of thing, you go back to your isolation forest and you are going to change the weights that led you to that decision. So you are going to recalculate your weights in a way to give more preferences to anomalies that you are interested in and less preferences to anomalies you are not interested in. So this is the first, the ISNAD team has been working on this for a few years now. This is one of the first results that was published. So in here is a comparison between the active part in the lower branch and the static part in the upper branch. This was Open Supernova Catalog, 2,000 objects only, very simple data set, but it was a supernova data set. So in this situation, binary microlensing event was an anomaly, an scientifically interesting anomaly. And you see that if you only use a static isolation forest, this object appears in number 33. And if you use an active anomaly detection, this object will appear in number 14. So if you account that in the real scenario, each one of these boxes is time that you are spending to go to a telescope and ask for spectra and do all of the classification purposes from 14 to 30, from 33 to 14 is a huge improvement in your allocation of resources. So the point is that there are many problems with the unsupervised learning scenario, especially for anomaly detection. The first problem is that this requires domain experts who not necessarily are familiar with the code and what the machine learning is doing. They need to interact very closely. They need to be able to say yes or no, and this needs to be smoothly went into the training procedure. So we need a whole infrastructure that is necessary, and Konstantin also told you about this in his talk yesterday. And in order to develop this environment, it is very important that these experts, they are involved in the initial stage of development of each code. This is a huge exercise of patience and diplomacy, but it's super important because they will guide the developers on what is necessary and what is not necessary to do. And the answers that they provide needs to be easily to reuse. So these are a few of the objects that we took all of this machinery now, and instead of applying to the Open Supernova Catalog, applied to the ZTF data, as Konstantin told you yesterday. So these are a few objects that are there from the ISNAD catalog, and one of them is this ISNAD 160, which is very large superluminous supernovae, which we thought was interesting to report in separate. And then the question that comes is, why do we thought it was important to report this? It's because in our group, we had experts that had some familiarity with this area of expertise. And this is something that is really important going forward. So for the unsupervised learning scenario, in preparing for LSST data, the things that we have to take into account is optimization and scalability of our code, prevent the loss of transients that already happened previously, especially for this superluminous supernova, which is super slow, and they depending on quality cuts or when the template image was taken, they even appear in the alert stream. So we should make sure that we have strategies to prevent that. Feature extraction, again, is still an issue. And also we have to understand how we can optimize the information given by the expert once they give you an answer of a given object. This is absurdly complicated because first, people change their opinion. So after you look a lot of times to the same thing, you will have a different opinion of this, but it is very important that we can reuse the information given by the experts so they don't have to look through the same object again and again and again. And obviously going to the live thing.
2
Yes.
minutes to go.
Yeah,
Just
yeah.
letting you know you have 2 minutes. Great.
Yeah. Thank you. Yes, I'm almost done. So, okay, and obviously the next step is to go to life transient, depending on the community decision on it. And this is a very important thing. This is my very last point that I want to talk to you, because I started this talk talking about what are the roles of recommendation systems, why does the systems exist, and how they can help you do our science better. And I think that the answer to that question is that recommendation systems, the main role that they have is to filter things that we are able to give meaning to. Otherwise, even if it's a super absurdly a new object, we will never be able to add meaning to it and make that into a scientifically discovery. And for me, this is as much a social issue as it is a computer or a programming one. I would say that as important as understanding your machine learning application, it is important to understand how the community that will give meaning to your output works, and how that interaction can be constructed from the very first time that you start developing these objects, these systems. So that's all that I had. Thank you very much, and I'll take questions if you have them.
Thank you for a wonderful talk, and we have time for questions. We have, let's start with a question online. Richard Kessler has a question.
Yeah. Hi, Emily. Thanks for that presentation. I have a suggestion as far as the recommendation for spectra. So my concern about the impact on cosmology is it's actually too difficult to do in real time, because I think that would require a full systematics analysis, which I don't think is realistic to do in real time. But I think something that is more feasible is to focus on the accuracy of a classifier. And SNN, for example, has tools to actually tell you that. So if a classifier says the probability is 0.6, do we mean 0.6 plus or minus 0.1 or 0.6 plus or minus 0.6? And really focus on getting those accuracies improved, and that will help the cosmology. We're sure of that, just as we're sure that improving calibration will help the cosmology, even though we don't have a real-time monitor telling us, oh, your figure of merit just went down because you improved. We know it's going to happen.
Yeah.
Okay.
Yeah. Sorry. Did I cut you?
No, I'm done.
Okay. No, thank you for the question. Yeah. No, I completely agree with you. So the problem here is that I completely agree with you that having meaningful probabilities for the classifiers will, like calibrated probabilities, will actually improve your cosmology in the end, and that's completely true. I agree with that. But if you have a classifier that you have to improve the probabilities on, there is already an assumption that you have a training sample. This classifier was trained somehow. And here, what I am talking about is one step before that. So the idea is to improve the training sample in a way that any classifier that would be built on that training sample afterwards would be better than another one which was built in a random sample. But I completely agree with you with the calibration of probability.
Okay, more questions. I see Gotham's hand up.
Hey, Emily, great talk. Thank you so much. A lot of the machine learning codes still have real trouble incorporating any concept of uncertainties. And in particular, if we're going to start doing anomaly detection with active learning, it seems like we need some way of actually modeling the fact that our data isn't perfect. Especially if we're going to go hunting for things like kilinovae, even the sky maps from LIGO get updated when you move from base star to LAL inference or whatever. So what prospects do you think we have for actually incorporating uncertainties in some robust manner into this entire active learning machinery?
Yes, so there are a few ways of doing this. The most traditional way, for example, this one, in this example that I showed you here, one of the things that they do here is like they use the uncertainties in the estimation as a proxy for what should be queried. So there are a few opportunities to use the uncertainty in the final probabilities, as well as if you have any estimation of the uncertainty on the real data. So what is more common is to use the uncertainties on the estimated probabilities. But we have a project inside NED nowadays that we are trying to, I'm not sure if this is what you mean, but what we are trying to do is like to give the expert the probability of not only saying yes or no, but giving some kind of level of credibility. So I think this is, I don't know, I'm 80% sure that this is, and the expert can make that decision based on whatever information he or she has, including the error bars in the data itself. So these are two possibilities that I can think of from the top of my mind. I'm not sure if I answered your question, sir.
We have time for one quick comment. I think I saw a comment pop up on the chat. Perhaps we could take that comment and then we'll move on to the next topic.
Yes. So so Kostya is just reminding that there is a feature extraction toolkit that was also developed within that, and if you have feature extraction in everything that I told you here, this is still a huge issue. So obviously there are classifiers that don't use features, but then they have other there's other issues that have to be taken into account. But if you are using features, we are super welcome to receive comments and bug reports and things on the feature extraction pipeline. So please, there is the link in the chat.
Great. So remind people that it's possible to continue the conversation on the Slack channel for this morning's session. And let's thank Emilie again for a great talk.